This is Bill Farmer again. Welcome back to McMaster University course, Computer Science 1JC3, Introduction to Computational Thinking. We're continuing with the last topic of the course, software development. We're going to start today talking about the development phases that are involved when we're producing software. Now, there's various ways you could define these phases, but I'm going to define the development process as consisting of 6 phases. And I'm going to go through each of these. The first is problem identification. This is a phase where we try to answer the question, what is the problem that needs to be solved? The second phase is requirement specification. Sometimes this is called problem definition. What are the product requirements that need to be satisfied? What objectives, functions, and constraints are relative? So basically, it's a presentation as a form of a specification of what the problem is, what we need to solve. And this is given using product requirements. And the next is design. This answers the question, how will the problem be solved? So the requirement specification is what is the problem? Design is how will the problem be solved? How will the product requirements be satisfied? How will we satisfy these requirements? The fourth is implementation. What is a solution to the problem? What is an executable implementation of the design? And the fifth is testing and verification. What behavior does the product exhibit? Is the product correct? And 6 is delivery and maintenance. How will the product be delivered and maintained? Now, the really crucial part of this, in many ways the most crucial part, is number 2, requirement specification. Because everything depends on the requirement specification. The design has to be a design that satisfies the requirements, and implementation should be something that satisfies the design, that satisfies the requirements. So indirectly, the implementation must satisfy the requirements. Testing and verification are done to make sure that the implementation and design we produce satisfies the requirements. And delivery and maintenance are really concerned about making sure we continue to satisfy the requirements. So this is the most important part. And I will just say the interesting thing and sad thing about software development is most software products do not have any requirements. So another way of saying that is most software development does not follow the most basic principles of software development. Now there's many different models for developing software, and I'm going to talk about a few of these. The first is the most famous. People talk about this all the time, the waterfall model. How does this model work? We just follow these phases. We identify the problem, we write up a specification of requirements, we produce a design that satisfies the requirements, we produce an implementation that satisfies the design. We do a bunch of testing and verification to make sure everything's okay. And then we produce a plan for delivering and maintaining it. That is the waterfall model. Now, this is a very useful model, but it is completely an idealization. It is almost never the case that software is developed in this way. There's all kinds of reasons why this approach fails. I'll just give you an example. We write the requirements spec, we start working on the design, and we realize that some requirements are missing or some are wrong. We got to go back to 2 and rework on that. So with the waterfall method, you're sort of going like this. You start up here with problem identification, requirement spec, and eventually you get done. You don't go back, but usually you need to go back because in the process of doing the software development, you find things that are wrong. You have to go back and better understand them and fix them. So the waterfall model is very useful, it's very convenient, but in reality, it is not really a real software development model. Another model, which is closely related to the waterfall model, is the spiral model. So the spiral model works like the waterfall model, except we start with 1, we go to 2, we go to 3, and if we need to, we go back. So basically, we're going like this. We're constantly going back and revisiting these phases. And we keep doing that until we get a suitable product that's obtained. Now, the refinement model is a model where we start with our spec, requirement spec, and then we refine that into some kind of design. And refine means we add new ideas, new ways of doing things, like it could be in the requirements. It says we have to do something. The first step is we're going to do this by having 2 modules interact. And then we can say what these modules will look like, and you keep refining. So we're making things more and more refined until finally we get to our product. So that's the refinement, and this is a top-down approach. Many people who like to develop software in a very careful, formal way like this approach. Another approach is called prototyping. So prototyping is we make a prototype of the product, we develop it, and then when we're done developing it, we throw it away. The reason we throw it away is because we're assuming, if you're using this approach, that we don't really understand the problem completely. We need to build something to understand the problem. We build it, we learn better what the problem is, and then we throw it away and start over again. The next model is the incremental model. This is a model where I had suggested when you do your software development for your assignments, you do it this way. So this kind of model is you take you get some of the requirements, you get some of the design, some of the implementation, some of the testing and verification, and you get a product that works. It satisfies some requirements. And then you try to expand each of these. So you're incrementally getting closer and closer to the full requirements, to the full design, full implementation, full testing. This can be a very effective approach because you get things running right away and you have a sense of what is working and what isn't, and you can slowly, incrementally approach the full product. The last approach, the agile approach, this has become more popular recently. Here, the product evolves through a dialectic between the client and the developers. One of the most difficult problems in software developing is figuring out what the requirements are. And you would think, well, you go to the client wants to build a piece of software, you ask them, what are the requirements? It's very likely that the client can't answer that question. They don't really know what the requirements are. They may not even know exactly what they want. So it's very hard to develop software, good software, if you don't know what the requirements are. Or even worse, you have to guess at the requirements and you guess wrong. So the agile approach, this approach is that the developers, they just develop something quickly. They show it to the client. Is this what you want? What's good about this? What's bad about it? And the client reacts, and then the developers develop something more, or they expand it or modify it. So you have the client and the developers. So they have this dialectic. They're going back and forth between the two. And many people argue this is a faster way to get a product that meets the needs of the client. What bothers people about this is that you may not end up with a clear set of requirements in the end. So these are just snapshots at different kinds of software development models. real software development models that software development houses use are very detailed. They have many aspects, and they probably use parts of these kind of models. Okay, so let's move on to a big question. What is software engineering? So it's an area of engineering that deals with the development of software products, but not just any software products. I mean, lots of people develop software products, but where you really need software engineering are products that are large or complex. They exist in multiple versions. So there's not just one version of your software, you have multiple versions. They exist for long periods of time, years or decades. They are continuously being modified. Often they're being modified because they depend on other software products, and these are being modified. And they are built by teams. So software of this kind, we need software engineering. Now, according to IEEE, software engineering is the application of a systematic, disciplined, quantifiable approach to the development, operation, and maintenance of software. That's the kind of definition you could give for any area of engineering. Now, we talked last time about David Parnas in 78, and I mentioned he's one of the fathers of, he's really the father of McMaster software engineering program. He said that software engineering is multi-person construction of multi-version software. The reason he said this is things really get difficult to handle when you have a software project that involves multiple people or multiple versions. So that's why he emphasizes those 2 points. Now, like other areas of engineering, software engineering relies heavily on mathematical techniques. See, we want a quantifiable approach, and we want it to be disciplined. So, and systematic. All of these suggest we want to use mathematics. Now, what makes software engineering different from other areas of engineering is the mathematics is different. In most areas of engineering, the main kind of mathematics that is used is what's called continuous mathematics, calculus and analysis. But in software engineering, the main kinds of mathematics are logic and discrete mathematics. So you'll be taking other courses in those areas. So I want to talk a little bit about some of the main software development principles. I'm going to very briefly talk about 9 of these, but go in more depth about some of them. The first principle is rigor. With rigor, we want reasoning to be precise. There's separation of concerns, so different concerns should be isolated and considered separately. Modularity. We want to take complex systems and divide them into smaller parts called modules, and we want to build complex systems out of these modules. There's a principle of least privilege. We've already talked about this principle. Each subject should be given the fewest privileges needed for it to get its job done. There's formality. Reasoning should be done using a language with a formal syntax, so we can manipulate the language by software, and a precise semantics, so we know what things actually say when we write them in language. Abstraction. Abstraction is separating out what is important from what is irrelevant. Anticipation of change. We want to be able to anticipate what is going to be future change that's relevant to our software and plan for it. Generality. We always want to solve a more general problem than a more specific problem. This is because our problem may change, and we still want to be within a solution. And also, if you have a more general solution, you have a more powerful solution. And the last is incrementality. We want a problem that can be attacked by producing closer and closer approximations to the solution. Many problems are just too hard just to solve them in one fell swoop. Okay, so I'm going to talk about some of these in more depth. And the first principle is separation of concerns. So this is a very basic principle used in engineering and used in everyday life. It's the principle that different concerns should be isolated and considered separately. So the goal is to reduce a complex problems to a set of simpler problems. So we solve these simpler problems, and then together we solve the complex problems. And this enables parallelization of effort. So this means we can have several people working in parallel on the problem because they're each handling their own concerns. Now, how concerns are separated, there's many different ways. Concerns can be separated by different times. So if you have a software product, one concern may be what happens when you start the product up, what happens later when you turn the product off. So you can separate concerns by times, you can separate them by qualities. Qualities like space efficiency or time efficiency. Software system can also be considered from different views. Like, what is the view of the user? What is the view of the developer? What is the view of the maintainer? And finally, you can separate concerns in the most obvious way by parts of the software system. So for instance, you could have a part that deals with input, a part that deals with processing the input and producing output, and finally the part that handles the output. Now, separation concerns does involve some dangers. One is that opportunities for global optimizations may be lost because you're looking at things separated. You're not looking at them as a whole. And I would argue that in real life, many of the most difficult problems to solve are problems that are not able to solve using separation concerns. They're problems that are complex. They have to be solved, a whole series of problems together. Another danger is that some issues just can't be separated out. They can't be isolated. And we've already talked about one such issue, security. Okay, another important software engineering principle is modularity. So a modular system is a complex system that's divided into smaller parts, and we call these parts modules. And modularity enables the principle of separation concerns in two ways. So different parts of the system are considered differently, and how we consider the parts and how we compose the parts are considered separately. So this is how modularity works in these two ways. And we have modular decomposition and modular composition. Modular decomposition is a top-down process where we take our system, break it up into modules, then we break those modules into submodules, and we break those modules into sub-submodules, and so forth. So this is a kind of divide and conquer approach. We make the problem easier to deal with by breaking into smaller pieces. The other approach, modular composition, is bottom-up. This kind of approach, we make small modules, and then we put these together to get bigger modules, and we put these bigger modules that get together, get even bigger modules, until finally we get our product. And the crucial thing about modular composition is we're thinking of these modules as interchangeable parts. It's like you're building a house, and you're building it from interchangeable parts like bricks, 2x4s, windows, doors, and so forth. Okay, so I have a question for you now. Question about modular units in Haskell. What are used as modules in Haskell? And you have 5 possible answers here. I'll give you a moment to try to answer it. Okay, welcome back. Well, in Haskell, functions are very, very basic in Haskell. Modules that are associated with files are important. Types, type classes, all of these are important, and all of these really are modules. They're all different kinds of modules. Notice one of them is actually called a module, but the other things are modules as well. Okay, so the real answer, I should have circled this. This is the real answer. Okay, I want to talk about another principle, very important principle. This is the principle of abstraction. This is a principle that we see in mathematics all the time, but this principle you can apply in almost any discipline. So the principle of abstraction is to focus on what is important and ignore what is irrelevant. That's the whole principle. Find out what is important and wash away or leave behind what is irrelevant. So this is a special case of separation of concerns. We're separating what is important from what is not important. And this produces a model where we've left out, as I've said, irrelevant details. And so you can produce many different models of some entity with abstraction by leaving out different details. So the model you produce depends on what you're interested in. So something that may be a detail that you care about in one situation, you may not care about in another situation. So there's many different abstraction models. And if you take an entity and produce an abstract model from it, then you can produce an abstract model from that and so forth. And this produces a hierarchy of models. And you can think as you go up, they get more and more abstract. As you go down, they become more and more concrete. And refinement, which we talked earlier about as a model of software development, refinement is the opposite of abstraction. Abstraction is getting rid of details. Refinement is adding details. Now, one danger of abstraction, which you probably all experience, is that if you over-abstract, you produce models that are very difficult to understand because they're missing too many details. There's not enough detail so you can connect to it. It just seems like it's floating in some kind of reality that's not connected to what you understand. But anyway, I want to emphasize abstraction is an extremely powerful principle of development. Okay, we're going to look at one more principle, anticipation of change. Now, let me say that one of the great dangers of software is that a client needs some software, let's say the government, they get someone to design and build it for them. It costs a lot of money, maybe millions of dollars. They produce the software, and the software has to interact with an environment, which can be other software, physical things. It could be software in a car or plane. And over time, things change, and the software may not be able to change with it. And it could happen at some point. The software starts suffering from old age, and at some point it just dies. And your dies in the sense you can't use it anymore. So your $1 million of investment in developing software are lost. So anticipation of change is very important. Our world changes very fast. Software, to be successful, has to change. In order to produce software that can change, we have to anticipate what changes will happen. So I'm going to mention 3 techniques for dealing with change. The first is configuration management. So we manage the configuration of our software in an effective way. So as the software evolves, we can modify the configuration. So this is a straightforward, obvious way. The second way is what I've already mentioned earlier, is that David Parnas has been one of the developers of, and that's information hiding. The idea with information hiding is we hide things that are likely to change inside modules. So you could think of a picture here. We hide something in here that's likely to change. I'll call it X. So this X may be something like how we store certain information. That we think how we're storing it now will be different in the future. We're going to store it differently in the future, but right now we're storing it a particular way. We think it's likely to change. So we hide it in a module. Now there's other modules who use this module. They're going to use this module, but they never really see or know what X is. It is hidden from them. It is hidden. And the wonderful beauty about this is that we thought X is going to have to change at some point. It does change. It becomes Y. But this module down here doesn't have to do anything. It doesn't have to make any changes because it never knew about X anyway. So it couldn't rely on X. It couldn't use this X that was hidden from them. So when X is changed to Y, your software keeps working. So this is the power of information hiding. The last one, which we've talked about already, is the little languages. So here, we anticipate change by thinking, well, we're trying to solve a problem. This problem may change over time to a different problem. So let's not just solve the initial problem. Let's solve a whole family of problems that are likely to come up in the future. And we'll solve this whole family of problems by building a little language. So I want to just end by saying software is constantly changing. The world that it's being used in is constantly changing. Anticipation of change is crucial for the software development process. Okay, we're going to stop here. And we'll continue next time with testing. See you then.